Hi, welcome back. Let's begin looking at the convolution operation, and we're only going to start in discrete time. And it's going to take us a few videos, I think, to fully understand this operation. And remember that the example videos are optional. And if you're not watching the example videos, and if you're ever going to watch an example video, it should be the ones on convolution. You'll want to make sure that you work out some of these on your own. Okay, so let us get started. Now, first recall in discrete time that any signal x of n can be written as a sum of a bunch of scaled, shifted impulses. Okay, so for example, I have this x of n here, and there's nothing particularly interesting about this x of n. It's just a general one. Okay, so it can be written as a bunch of these little signals, shifted, scaled impulses added together, right? So for example, at -2, I've got a -1 down here. So that contribution is due to this impulse. This impulse is -1 times delta of n plus 2, right? Advanced by 2 units and scaled by -1. Okay, this sample here at -1 is -2, so that impulse, if I add to it a impulse that is advanced by 1 unit, scaled by -2, okay, then I'll have the first 2 samples. And if I keep going all the way up to, in this case, the n equals 3 term, which is a 3, I'll have a delayed impulse by 3 units times 3, scaled by 3. And I add all those together, and I've got the original signal. Okay, so and of course, I don't want to worry just about this xn. I want to just be concerned in the general case. So in general, any discrete time signal can be represented like this. K goes from -infinity to infinity of x of k times delta of n minus k. Okay, that's the first thing that you need to be concerned with and comfortable with here. You say, where did these infinities come from? Well, in my example here, the infinities are just to cover our bases for any signal x of n. In the example that I have here, x of 4, x of 5, x of 6, all the way to infinity are 0. So they contribute nothing to this sum, which is why I don't even need to write them here. Same thing with the x of -3, x of -4, x of -5 to -infinity. They are 0, and they contribute nothing to this sum. But in general, I don't know when my signal starts, and I don't know when my signal ends, and so I have to consider from -infinity to +infinity. And so, just so you're comfortable with the sum, if you expand it a little bit, you'll notice that, well, if I look at the k equals -2 term, this is x of -2 times delta of n plus 2. And what is x of -2? Well, x of -2 is -1. So this k equals -2 term, that's exactly this signal here. -1 times delta of n plus 2. And then then after that would be the k equals -1 term. Okay, x of -1 times delta of n plus 1. So x of -1, so -1 is -2. So that's exactly this term here, and I would keep going and so on. I think you get the idea. Okay, so this is the first thing that you need to be comfortable with. And actually, I am going to write out a few more terms here. So let me do that. So we would have the x of 0 term, delta of n, plus the x1 term, the k equals 1 term, delta of n minus 1, and then so on. Okay, now let's say we put that signal into a LTI system. So I'm going to represent that like this. This box is my LTI system. And I want to know, what do I get out? Right? Why then? What do I get out? Well, to answer that, let's simplify the problem first. And let's say I put in an impulse. I put in an impulse into the system. Okay? And then I just look, what do I get out? So it's kind of like an experiment. And I see that I get something out. And we're going to represent that something with the letter H. Okay? So we just put this very simple signal in, a delta function, an impulse function, in just a small disturbance into the system at time n equals 0, and we see what we get out. Okay, this is like probing the system. If I give a little disturbance, what do I get out? So we're going to call this H the impulse response. And in our course, H, lowercase h, will always mean the impulse response. I don't know why we use H, but that's just that's the way it is. Okay, so that's the impulse response, and you'll hear me say impulse response quite a bit in this course. And you can think of it as literally the response or the output to an impulse, an input of an impulse. So I put an impulse in, I get an impulse response out. What do you get out? Well, the specific impulse response depends on what the system is. Okay, but let's say that's known. Let's say it's known that delta of n produces this h of n, whatever it is. Okay, so this is also given. This h of n is given, and also given is the fact that the system is LTI. Now we're going to try to answer our original problem. What happens when I put in just any old signal? How do I find the output? Well, because the system is linear, I can consider each one of these constituents of the input separately, right? Remember what it means to be linear. I get the same mixture out as I put in. So first of all, let me just consider this piece, right? So this is nothing but a constant like alpha times a signal, right? X of 0 is 1, it's a constant. And here's another constant, X of 1, maybe beta, times another signal, right? And so what we showed with linearity was that you can consider just each piece separately because you're going to get the same mixture out. So let us determine, well, what do we get out when we put this constituent in? Okay, and the reason I'm starting here is because this is a simple little delta function. So what do I get out when I put in that little signal? Well, we said when I put in a delta function, I get this h out, the impulse response. And this is a constant. Because the system is linear, you get the same constant times the output out, right? So if delta produces h, then a constant, this is the scaling property, a constant times delta produces that constant times h. So this is what we get out due to this term in orange. Okay, and then I might consider this term. What do I get out here? Well, this is not a delta function. This is a delayed delta function. But if the system is time invariant, you see, then what I get out from the delayed delta is a delayed impulse response, right? We said if it's time invariant and if delta produces h, then delta of n minus 1 produces h of n minus 1. And because it's linear, x of 1, that constant, times delta of n minus 1 produces x of 1, that same constant, times h of n minus 1. You see where we're going with this? So we can apply the same kind of argument to each one of these terms, you see. And in general, the kth term produces x of k times h of n minus k. Okay, so that's in general. So the output, I'm running out of room here, so I'm going to erase some of this. So the kth term of the output is this thing here. So what I get out, y of n, is a bunch of terms. Then there's the k equals minus 2 term. The k equals minus 1 term. This should be, let me back up, this should be 2. Okay, the k equals minus 1 term, h of n plus 1. The k equals 0 term, h of n, right? H of 0, yeah, excuse me, h of n. The k equals 1 term, and so on. And so we can write this compactly, and we could say that y of n is equal to a sum from k equals minus infinity to infinity of x of k, h of n minus k. And that is the big result here. That is a big result for our course. This says that if I have an LTI system and I know how it responds to just a little small impulse, then I can get what the output is due to anything. I just have to perform this operation of that input x with the impulse response h. And this operation here, this is an infinite sum, and then there's some multiplication. That operation, that's what the mathematicians call convolution. So in particular, because we're working in discrete time, this is discrete time convolution. And we write it like this, with this asterisk or this star. That's the convolution operator. So those two things in the box, those are equivalent. This on the left, this is a function of n, you see, because when I plug in values of k, right, k goes from minus infinity to infinity, the k's go away. You know, I've got the k equals minus 2 term and the k equals minus 1 term. And so what I get is a function of n here. So I can write that like this instead. And we would read this, y of n is the convolution of x with h. And that is our big, huge result here. I can't say that enough. Okay? And so that's it. That's the convolution operator. That's the convolution operation in discrete time. So now the next set of example videos that I have for you are just going to be working on calculating that sum for different inputs and different impulse responses.